For further discussion of the viewpoint of view, we take this circuit as an example. In last week's lecture, we introduced two standard methods for solving circuits, that is the node voltage method and the loop current method. We use the node voltage method to solve this circuit. Suppose this is a reference node, then the circuit only has one unknown node voltage. In other words, as long as we find the node voltage, we can find any branch variable from U. Now we write out the node voltage equation. The left side of the equation is 1 over R1 plus 1 over R2 plus 1 over R3 times U. The right side is US1 over R1 plus US2 over R2 plus R times I1 over R3, where the current-controlled voltage source is regarded as a voltage source firstly. Then we use the node voltage to represent I1. It's US1 minus U over R1. By replacing I1 with the expression and putting the equation in order, we get that 1 over R1 plus 1 over R2 plus 1 over R3 plus R over R1 R3 times U equals 1 over R1 plus R over R1 R3 times US1 plus US2 over R2. We will get all branch variables of the circuit by solving the linear algebraic equation of U. Now we find that the equation is just y equals a times xi plus b times x2 discussed above. Y is this, x1 is this, and x2 is this. The coefficients a and b is determined by this. According to the previous lecture, y prime equals a times x1 and y double prime equals b times x2. Y equals y prime plus y double prime. So how to represent these statements using the circuits? Look at this circuit. In this circuit, x1 equals 0 and x2 is unchanged. This is a reference node, and this node voltage is U prime. By applying the node voltage method, we get 1 over R1 plus 1 over R2 plus 1 over R3 times U prime equals US2 over R2 plus RI1 over R3. The I1 here equals minus U prime over R1. By putting the equation in order, we get that 1 over R1 plus 1 over R2 plus 1 over R3 plus R over R1 R3 times U prime equals US2 over R2. You see, the equation is satisfactory. It means B times X2. Then we focus on another circuit in which US1 is active alone and US2 is deactivated. This is a reference node. This node voltage is U double prime. By applying the node voltage method, we get 1 over R1 plus 1 over R2 plus 1 over R3 times U double prime equals US1 over R1 plus RI1 plus over R3. The I1 here is US1 minus U double prime over R1. By putting the equation in order, we get 1 over R1 plus 1 over R2 plus 1 over R3 plus R over R1 R3 times U double prime equals 1 over R1 plus R over R1 R3 times US1. You see, the equation is just y prime equals AX1. Then we get the conclusion that the solution U for the former circuit can be the sum of the solution U prime of this circuit and the solution U double prime of this circuit. In other words, U equals U prime plus U double prime. Since this circuit is very simple, it seems that we need not use this complicated method, but in the following learning, you will find that it's convenient for the circuit analysis by setting one source active alone and the other sources be deactivated. Now we introduce the superposition theorem formally, which means in linear circuits, any branch variable is the algebraic sum of the sub-branch variables, which are the superposing effects of every independent source. Although the description is complicated, you've known how to apply it by the example above. The superposing effect or independent effect means one independent source takes effect and others not. What's the meaning of the non-effect for the independent sources? For the voltage source, it means its value is zero. We've introduced previously that a voltage source with zero value is equivalent to a resistor with zero value and is equivalent to the short circuit. For the current source, it means that a current source with zero value is equivalent to a resistor with infinite value and is equivalent to the open circuit.